everybody, welcome to CS61B Discussion 8 walkthrough. Today we're going to go through the second half of asymptotic or algorithmic analysis. Some announcements first, congrats on surviving Enigma, and there are some assignments due this week and next week that you should be aware of. Let's get into the review. So we covered most of asymptotic analysis last week, but we're going to add some spice this time with best case versus worst case. So best case is a situation where you're restricting the examined situation to only the best case independent of input size. And you'll see what that means when we go through some examples. So basically, there are things that can influence the speed of the program, such as maybe the program takes n squared time when the input is odd, but n time when the input is even, that are independent of size, because odd numbers and even numbers can be any size. So when we're analyzing best case or worst case, we're basically analyzing on the assumption that we're going to get everything, either the best or worst possible case for anything that doesn't depend on input size. Now, best case, worst case, and average case can all be bounded by theta, O, or omega. This is important because they are similar concepts, but you shouldn't get those two confused. One key difference is that O and omega are not necessarily tight bound, so O is not the tightest best case bound, but when you say best case, usually you want a tight bound. Same with the worst case. If you're still confused about that, that's totally normal. I recommend that just keep an eye out that when it says best case or worst case, a lot of times it'll also say what kind of bound it wants. And a lot of times when it doesn't, you should be going for the theta case unless it's physically impossible. So going after that, let's get into the worksheet. So we're going to have just a bunch of problems today that are pretty similar in terms of looking at code, but they will be great practice. So the first one is an iteration-based problem. So this is kind of a warm-up. Let's provide the best and worst case runtime in theta notation for this. I'll give you a chance to try it out. Okay, let's go over it. So in this case, you notice that int I is independent of n. So we're doing this based off of n, which is the input size of our array, not I, right? So what this means is that this for loop, which starts at I and goes to n, can take variable lengths of time. Now, if I starts off equal to n, or less than n, it'll run no times because it'll immediately trigger this loop, not once. But regardless, that'll mean it'll take constant time. So our best case is that it takes constant time to run, because if I is equal to n, then no matter what, this loop will run the same amount, which is never. Now, in the worst case, if I starts off equal to 1, which we'll do because we're assuming that I is greater than 0 from the start, then it will run n minus 1 times, and that is the worst case. So in that case, the worst case runtime is theta of n. Now notice that we're looking at these two cases of I being equal to n and I being equal to 1, but that doesn't actually cover all of the cases, and that's important. Best and worst case runtime don't cover every single case. They don't divide the space of possible experiences into two. They literally only take the best possible situation and the worst possible situation. And there are usually lots of situations in between where things can take some runtime in between those two cases. But for now, we have a best case runtime of 1 and a worst case runtime of n. So let's do another problem that has to do with iteration. So I'll give you a chance to look at it and then we'll go over it together. Okay, so let's go over it together. So starting off, we can find where our best and worst case is going to come from, which is this if statement right here. We don't know when or how SLAM determines when to return a true or a false, so we can assume that for the best case, this is always going to return true, which will cause us to break out of this inner for loop every single time without fail. So what that means is that if we always break out of the for loop on the first iteration, then this actually runs in theta of 1 time or constant time, because we're just going to be going da da and then break and immediately popping out. So if we have n loops from 0 to n, and then we go do theta 1 work inside, then the total runtime of this double for loop is going to be theta of n. This loop down here always takes theta of n time as well because we're going from 0 to 1000 times n, drop the coefficient, and we're adding 1. So together, the best case is going to be theta of 2n, which simplifies to theta of n. Now for the worst case, we'll assume that this is never true and that we never prematurely break out of this for loop. Well, one thing to notice is that this for loop doesn't look like a normal for loop. We don't have that first clause right here. Instead, j equals 0 is set on line 2, outside of this for loop. This means that this for loop is never reset back to 0. So once j hits m, it's never going back to 0, which means that this inner for loop runs m times in total, no matter what. And after it's done running those m times, every time we try to run the for loop, it'll do a single check, checking whether j is still greater than or equal to m, and if it is, it'll keep going. So we'll have this m inner loops, and once that's done, we're going to have n outer loops, where every time we check to see whether it's done, and if not, we go back up here, and we keep going. So the total runtime of this is actually going to end up being theta of n plus m. If you're unsure on how that works, I recommend you try it out yourself and see how it works with your own eyes. And again, the runtime of this lower function, the lower for loop, stays the same. So our worst case is going to be theta 2n plus m, which simplifies to theta of n plus m. Now let's do some recursion. So this is a kind of start with recursive problem. So I'll give you a chance to take a look, and then we will go over it together. Okay, let's go over it together. So in this case, this inner for loop is independent of n because j just goes from 1 to 1024. So there's no involvement of I or n in this inner for loop, which means it basically takes constant time. So the outer for loop goes from 0 to n in constant time in each loop. So therefore, the whole thing takes theta of n time to run. Now, each recursion does half as much work as the previous, so we can get a summation that looks kind of like this: n plus n over 2 plus n over 4, all the way to 1. This actually sums to 2n if you do the arithmetic formula, or no, it doesn't sum up to 2n if you do the arithmetic formula. This is actually Zeno's paradox, which is something that's very fun to look at. There's a TED Ed video about it that really stuck with me from when I was a kid. But yeah, if you do n plus 2n, n over 2 plus n over 4 all the way to 1, this will sum up actually to right about 2n, and that simplifies to theta of n. And if you want to have like a formula to do this, I think the summation formula results in something similar if you start with the 2 to the I formula. Because this is basically similar to what we did in the previous problem, where we do 2 to the 0 plus 2 to the 1, all the way to 2 to the log n. Same thing happening, but in reverse. I just thought pointing out that it was Zeno's paradox would be kind of fun. There's no condition here that's independent of n. There's no odds, evens. There's no math.random. There's no magical thing that pops in. So the best and worst case are going to be the same here, and they're both going to be theta of n. Now let's do another problem. This one's a little bit more complicated, so I'll give you a chance to take a look, and then we'll go over it together. Okay, let's go over it. So this for loop right here runs in theta of high minus load time. One thing important to point out is that the problem actually says that we are finding the runtime when we pass in R0n specifically. So that's important because otherwise this problem is a lot more confusing. So where this first for loop initially takes n time to run, and then as you can see down here, every time we call a recursive call on it, it takes half as much time. So we have math.random, and this is going to give us a random value between 0 and 1. So the best case is that we always trigger this first one, which will result in us only doing one recursive call, which is half the work every time, which is the same thing we saw in the last problem. So the best case runtime would be theta of n. In the worst case, we always trigger the second else, where we actually have two different calls, where instead, because each call does half the work of the previous call, and there are two calls being made, each level does n work. And in that case, we have n work and log n levels, because that's how long it takes for us to hit a point where high minus low is only going to be equal to 1. and that's going to be n log n. If you're confused, I recommend you draw out like a tree structure showing the recursive calls that are made, and you'll see pretty quickly where this is coming from. Now we'll get to another one. This one is more, again, another recursive example, so I'll give you a chance to take a look, and then we'll go over it together. Okay, let's go over it. So the actual work being done by each call here is very small, right? All it's doing is doing this one check and then calling again. So this all takes constant time. The big thing here, though, is that it's making 3 calls each time. And as you can see, this is the sort of structure that happens. So this first call takes constant time, and then each of its children takes constant time, but there's 3 of them, and each of their children, this level is 9, and it'll keep going up until we hit the nth level. So you can kind of imagine this as 3 to the 0 on the 0th level, plus 3 to the 1 on the first level, plus 3 to the 2nd on the 2nd level, all the way up to 3 to the nth. And this simplifies to theta of 3 to the n per the summation formula. There's a couple different ways to think about it. One way that people say is that 3 to the n completely dominates all the previous terms, which can be confusing because when you sum up 1 plus 2 plus 3, etc., that the last term there doesn't dominate. But the reason is because when you sum up every term previous to 3 to the n, the sum is actually less than 3 to the n. So the sum from 1 to 3 to the n minus 1 is actually less than just 3 to the n, which is why this last term kind of ends up dominating, causing the total runtime to be theta of 3 to the n. Of course, you can always just use the geometric formula to get this, and when you simplify, you'll get the same answer, and that way you don't have to rely on your intuition when it's not quite developed yet. Okay, let's do another one. So again, it's another recursive example. So we're trying to find the best and worst runtimes in theta notation for this problem. Okay, let's go over it. So here, let's look at this helper function first. So we can start with this for loop, since that seems to be like the juiciest part. Each run takes log of m time because we're basically going from 1 to m and we're multiplying by 2. And so now when we call these children, we're going to get this tree structure where this first call takes log m time. Each of the children also takes log m time because we notice we don't actually alter m in any way. And then we're going to keep doing that until we get to the level where n equals 0. So there's n levels, and in each of those levels, we have a node that we have all these nodes that take log m work. Now the total number of nodes in this entire tree is 2 to the n. I told you that this formula would come up again. So we're going from 1 plus 2 plus whatever all the way to the n. This is counting the number of nodes in this tree, and we're multiplying that by log m because that's the amount of work done. And this sums up to 2 to the n log m. Now, if you notice, when we actually call the recursive formula, we're calling m is equal to n divided by 2. So we just do 2 to the n of log of n divided by 2. That simplifies to just 2 to the n of log of n because we can get rid of lower order terms. And that is the runtime for this one. Now let's do one last problem. So I will give you a chance to take a look and then we can go over it together. Okay, let's go over it. So in this case, we have this for loop down here, which always runs in theta of low plus high divided by 2 based off of the formula we see on line 9. As you can see, we're passing in 0 and n at the beginning, which means at the beginning, this is going to take n over 2 time. And so in the best case, we just hit this target clause, the array mid equals target right away, and this is true. So our best case runtime is just theta n, where this takes a single recursive step, and basically we end up immediately ending. Now, the worst case is that we have to keep recursing until we hit this if statement at the top. So if in that case, we're going to end up with this tree structure. Notice that's actually not symmetric. And the reason is because I isn't going from low to high or something like that. It's going from 0 all the way to mid. And since we are setting low, mid, and we're setting mid to be high in the first call and setting high to be mid in the first call and low to be mid in the second call, the new mid is going to be n over 4 or 3n over 4, but the for loop is going all the way from 0 to that value each time. So basically this is doing n over 2 work, this node is doing n over 4 work, but this node is going to be doing 3n over 4 work. And same for all of these, which means the summation is a little less neat than we would like. So the first level does n over 2 work, but the second level does n work, and the third level does 2n work, and on until we get to the last level, which actually does n squared work. And again, you can see that if you count up the work on each of these levels as you go. And in that case, the total runtime will be theta of n squared in the end, based on what we've been talking about so far. And so the best case here is theta of n, and the worst case here would be theta of n squared. Congratulations on making it to the end. I wish you guys all have a good week, and I'll see you guys later.